Picture this. A child is lost in a large building. The searching teams start from the entrance, then check each floor room by room. They don't go randomly deep. They clear the nearest areas first. This is breadth first search. Prioritizing closeness and covering all possibilities at each level before going deeper. Hello, we are Team Sukuno, and in this presentation we will unravel the logic, power and applications of breadth first search, one of the most essential tools in data structures and computer science. Here's what we will be covering in this presentation. First, we will introduce you to the concept of breadth first search, what it is, where it applies and why it matters. Next, we will explain how BFS works step by step with an easy to follow breakdown of its core logic and structure. After that, we will dive into a code demonstration to see BFS in action, making the theory come alive. Then, we will explore some real world applications of BFS from network routing to game AI and beyond. We will also walk through BFS tree traversal, showing how it operates in tree structures specifically. And finally, we will wrap up with a quick conclusion summarizing what we have learned and why BFS remains a fundamental tool in algorithm design. This slide introduces graph, a mathematical structure made up of vertices and edges. The left box shows the adjacency list, which is a common way to store in a graph code. On the right, you can see the sum graph visually. Each arrow represents a directed connection, and yes, a tree is just a specific kind of graph that's acyclic and connected. So, what exactly is breadth first search? BFS, breadth first search, is a graph traversal algorithm. As we have seen from the previous slide, it's an algorithm designed to explore layer by layer, checking every nearby path before diving deeper and guiding you straight to the shortest possible route. Welcome. Let's take you to a real world example. Suppose you are on a social network and want to find out how closely you are connected to a famous person, let's say Elon Musk. You know some friends who know other people and you want to find the shortest path of connections to reach Elon. This is where breadth first search comes into play. It starts from you and explores all your direct friends first, then it moves on to their friends and so on until and unless it finds Elon. In this example, BFS finds a connection from you to Priya, then to Roger, and then finally Elon, the shortest friend chain.
So let's now understand the breadth first search actually how actually works. So breadth first search or BFS work in very systematic way. The main idea is explore the graph or tree layer by layer, meaning we visit all the nodes at one level before going to the next. To make this happen, VFS uses queue data structure. A queue works on first in first out principle, just like just like the people standing in the line. The first person to get in this first to be served. In the same way, the first node we explore get handled before the next. Now let's go through the actual step of the VFS algorithm. First, we enqueue the start node into the queue. That means we add it to the line and we mark it as visited so we don't visit it again later. Then we enter a loop. This loop runs as long as the queue is not empty, meaning there are still nodes left to explore. Inside this loop, we dequeue one node. That means we take the front node from the queue. Then we look all neighbors of the node. These are the direct connection node. For every neighbor that we haven't visited yet, we mark it as visited and then enqueue it so it will be explored in the next round. This process continues level by level until we either visit all nodes or in the case of search until we found our goal. Let's let's take a small real world example to make it clearer. Imagine you are trying to find the shortest route for your house to your friend's house. The road between location from a graph and each intersection is a node. BFS will start from your house, explore all directly connected intersection first and then go deeper only after checking all those. This is how it finds the shortest path by checking every possible way in layer. Now, why do we mark node as visited? If we don't, we might go in loops. For example, a node might link to a node B or a node A might link to a node B, which links back to A without marking. We'll just keep jumping back and forth between A and B forever. The beauty of VFS is its simplicity and order. It ensures that we explore the graph level by level without missing anything or repeating ourselves. In short, BFS uses queue. It explores all the neighbors before moving to the next level. It marks node as visited to avoid repetition, and it continues until queue is empty or goal is found. That's how BFF works.
Now I will give an example of breadth first search. We start from the starting node 1 and then we enqueue the first starting node to the queue and mark it as visited. How do we mark it as visited? We can mark a node as visited by putting it in a visited set. Set has membership test. It does the membership test very fast. Then we go with the main loop of our traversal. While the queue is not empty and the goal is not found, we keep on traversing the tree. So firstly, we go to the 2 node and the children of the first starting node is enqueued to the queue. And then here at the first 2, 3 and 4 is enqueued. Then 5, 6, 7, 8 is enqueued, the children of 2, and then we enqueue the children of 4. Here you can see how the traverser is going through the breadth of the tree. It searches in the first level, then the second level, then the third level of the tree. So firstly it checks 1, then 2, 3 and 4, then 5, 6, 7, 8, 9, 10, 11, 12, then 13, 14, 15, 16, 17, 18, 19, and at the last it checks that our goal is found. So this is a small visualization on the traversal, and here we start from the source. We go to 1, then go to 2 at the first level, then 3, then 4, then we go to the 5 and then 6 at the second level, and then at the 10 and 9 and 7 and 8 at the third level. So this way we traverse through the tree.
Okay, so from here I will walk you through a short Python code that performs BFS traversal on a graph or tree. So let's begin. So the first line of code simply means that we are importing a dequeue, which is a type of list that allows us to add and remove elements efficiently from both ends. We use it as a queue because BFS works level by level, just like standing in a real world queue. Here in this code, we define our BFS function. Here, graph is the data structure that holds the nodes and their connections, like a dictionary, and is assumed to be represented by adjacency list. Start is the node where we begin our search. Then, this code creates an empty set to keep track of the nodes we have already visited. We use a set because checking membership in a set is very fast with O1 time complexity. Then we create a queue with just the starting node. Now we enter the main part of the algorithm, that is the loop. This line simply says, keep going as long as the queue is not empty. If the queue has elements, we still have nodes to process. Then we take out the first element from the queue. This performs dequeue operation in the queue. Next, we check if we haven't already seen this code. That is the node we have just dequeued. We go inside this block. Here, we print the node to show we are visiting it, add it to our visited set,
so we don't visit it again. And finally, we add all of its neighbors to the queue, but only the ones we haven't visited yet. It's a bit long, but all it means is for each neighbor of the current node, if that neighbor hasn't been visited, add it to the queue to be visited later. So to summarize, we start with the node, visit it, then add its neighbors to the queue, then we move on to the next node in the queue, then we keep repeating until there are no more nodes left to visit. This is exactly how BFS works. It explores each level of the graph before moving to the next. That's the entire logic of the code. It's short, clean, and easy to use on both trees and graphs.
To conclude our presentation on breadth first search, we started by introducing what breadth first search is. It is a graph traversal algorithm that explores nodes level by level and searches for the goal until the goal is found. Then we looked at how BFS works. Actually, it uses a queue and it visits each node and explores all its neighbor before moving deeper. This makes BFS especially good for finding the shortest path in unweighted graphs. Then we also covered its time complexity, which is big O v plus e, where v is the number of vertices and e is the number of edges, making both of them efficient for graphs and trees. Then we walked through how it actually works with a clear step-by-step breakdown using a source example, and we showed how traversal happens from one layer to the next. After that, we moved on to some real-world applications such as web crawlers and GPN navigation and social networks. That's where the BFS is used to explore connections and shortest paths. Then after that, we showed a code demonstration of how BFS works in a tree, helping us to visualize the actual implementation. And finally, we explored BFS tree traversal, which gave us another practical angle of how this algorithm functions in hierarchical data structures. So to talk about this all in summary, BFS is simple, effective, and powerful, and it helps us understand graph structures, and it's widely used in real world tech. So yeah, that brings us to the end of our presentation, and if you have any questions or queries regarding to this, you can ask.